Welcome back. So let's do this half adder. Do this half adder or any other thing in CMOS. We require to have this Boolean expression. So we have in case of half adder, sum equal to A XOR B and the carry out equal to A percent B. This is Verilog operator for XOR operation. And this is Verilog operator for AND operation. So now what is that we are understanding from that sum is, if you expand that this XOR operation, A bar B plus A B bar. Kindly notice there is no bar here, top on the top. Here there is no bar. There is no bar here. So it means what? Without this bar, if you are designing CMOS circuit, then by default, CMOS will give inverted output. So CMOS by default, what it will give? Inverted output. So if you follow those rules to build that CMOS circuit, those rules means like first we have to start with pull down. If dot is there, then we have to connect the devices in series. If plus is there, then we have to connect devices in parallel. Then we have to take the dual of the given expression. And then again, we have to, by following this dot and plus convention, we have to build up pull-up devices using PMOS. That if you follow, of that output, whatever you get is inverted form, meaning some bar you will get. But we want some. So of that output, you have to just plug the inverter before, after that output, you have to plug this inverter. So then if you take the output of this inverter, then that will be actual output. So I will demonstrate that. So please watch carefully. So let's take here expression again. That is sum equal to A bar B plus A B bar. So what I said, first we have to start with the pull down section. In pull down, all NMOS devices will come. So if you look at this too, here is the dot convention. So it means A bar and B, they will come in series. So one device for A bar. This is A bar. And one device for B in series. This is series. Now, this, if you look at this one, I need two devices, one for A, one for B bar, and they will come in series. So one for A and other for B bar. And if you look these two, this one, first one and the second one, here we have the plus, meaning 1 and 2, this 2 will come in parallel. So that's why this way we have to connect. They are in parallel. Now, take the dual of this expression. So if you take the dual of that expression, it is A bar plus B in the plus will become dot, and then A plus B bar. That is the dual of that. Now with this dual, what we have to do, we have to start a pull-up section. In pull-up, PMOS devices will come. If you look at this one, this first one, let us call it as the first one. A bar plus B. So they will come in parallel. So we have A bar and a B. They come in parallel. This is your A bar. And this is your B. So in parallel. Now, if you look at this one here, call it as the second one. A plus B bar. Plus is there, so they come in parallel. So that is A. So we have to keep here this bubble for PMOS device. Here also have to keep. So, let's do that. So now this one A has come and B bar. This is B bar. They come in parallel. Now, if you look at 1 and 2, in between dot is there. So they come in series. That's why let's imagine in mind this entire thing is one resistor. This entire thing is another resistor. Series means like this, right? So that's how series. Now this has become the pull up. This is completely uh, pull up section, this one. And this is pull down section. Yes, let us take another cover. So this is completely your pull down section. So we have to join this pull up with the pull down. So let us join that here. Where you are joining, there where you take the output. This is your output. So let's call this output sum bar, because as I told, inverted output it will give. We do not have the bar here on the expression. So what comes is inverted form. So if there would have been bar, it is already inverted, right? So then this bar is not required. Since there is no bar on the expression, so what we get is the bar one, that is inverted one. So few more things to complete here. That is VDD you have to keep give here, that is this one. So here VDD. So this one is VDD. And here ground, pull down here ground. And of course, this bulb needs to be connected to the source here. Bulb you will connect to the source in case of this MOS here. This is the source down here. And in case of PMOS also, you will be connecting to the source again here. And anything left here? Yes, we have to get this A bar and B bar. So it means what we need one inverter, right? Here, if you look at this A bar is required here. And if you look at this one here, B bar is required. Even here, this this one, B bar it is. So it means what? We need one inverter. So let's do that here. You know, inverter already we have done in experiment one. Simply PMOS and NMOS in series and connecting their gates, NMOS to the ground, PMOS to the VDD. So here if we give the input A, what you get is A bar. Similarly, for B bar also, same one more inverter you take, you connect and you give here B. This is your VDD, this is ground, and here what you get is B bar. So you got A bar, B bar, and one more inverter is required here at the sum. To get this sum, we need one inverter because it is sum bar. So this is one inverter here. So output of this inverter is sum. If you connect this sum bar here, so that's the idea. So now you can see this whole picture. So this is from this inverter we are getting A bar. A is there of course, and from this picture that is this inverter we are getting B bar, and B is there of course, and this entire circuit is going to produce sum bar for us. Now this sum bar is given to the inverter, and we are getting the sum here. So now what is required is this carry out is required. So that is A and B. So how do we do? A and B means A dot B, right? Carry out equal. So it is again the same. We do not have the bar here. So because of this dot convention, we have to start with the full down section. Because of the dot, we will get two NMOS devices in series. This is your A, this is your B. Now, what you have to do, you have to take the dual of this, A plus B. So, since plus has come, you have to connect them in parallel. See how parallel is. Like, this is how the parallel is. So, now connect this parallel devices and pull up it is. So, give it to VDD. And join this pull up section with pull down section. Where the join is happening, the demarcation, there you take the output. So let's call this as a CO bar. And this is your A and this is your B. Why I'm saying this CO bar? So at this point of time, for everyone, it must be clear because there is no bar here. By default, CMOS will give us the inverted output. So if there would have been bar, so it means it is already inverted output. We have obtained. So you don't need to give the CO bar. CO is enough because CO is equal to this inversion, and under that this A dot B is there. Na? By default, CMOS will give inverted output. So it means CO only this. But now if you look at that actual CO, what is carry out? A dot B. Is there any inversion here? Bar? No bar. But by default, CMOS will give inverted output. So it means what it has given? It has given CO bar, but we are looking for CO. So that's why we need one inverter at the output side. And you connect this one here like this. And this CO bar you will be giving here as an input to this inverter. Of course, here VDD and ground are required for the inverter also. And this is your CO. Okay. So now this PMOS bulk is connected to the source PMOS source, and the NMOS bulk is connected to the NMOS source. And the last NMOS is connected to this ground. So that's how we have our carry out. So now you can see but sum, that's how you are obtaining, and this is your carry out. Okay. So let's do this one now in LTSpice. So on LTSpice, here this icon, double click this one. Go to this icon schematic. Now what is required you know already. So that is we need here, look at this to implement sum. We need here 1, 2, 3, 4, 4 NMOS devices. Okay. The way I have connected discussed here. So you should keep in mind that. So let's take this. Let's go to NMOS. One NMOS here, and another NMOS here, one more NMOS here, another NMOS here. Okay. So now if you look at this one, we also require NMOS here to build this inverters here at the output side, one inverter here. And to carry out also we need NMOSes. So first I will finish this sum, then I will come to this carry out. For now I need 1, 2, 3 more NMOS. So one NMOS here. So NMOS here. Okay. So now go to the again component, pick this time PMOS. Now if you look at this one here, PMOS, like the side by side I have required to be kept, that is in parallel. So let's do that. That is one here, one here, one here, one here. And the one for this inverter, the other for this inverter. And then one for this inverter. Yes. Okay. Now, let's connect this in series. This is also in series. And here, this NMOS devices, they are in parallel. This one in parallel, this one. This one parallel. And here, these two in series. And here, this pull-up section needs to be connected to the pull-down. And where we are connecting this pull-up and the pull-down, there where we take the out. And then little wire I'm extending here from this gate of this every device. So this how I'm connecting, I already explained in NAND gate experiment too. Just left click, hover the mouse where you want to stop there, left click and right. See here left click and then hover the mouse. Here I want to stop, left click and then right click. That's all. this. This bulk required to be connected to the source in case of NMOS and in case of PMOS also connect to the source. Now extend this one thing and extend this one here for A and A bar and for B and B bar. This is for the ground here. So, and this output side also let us connect this. Extension within PMOS bulk connected to the source here. And once also going to be connected, its bulk to the source here. Now, almost done. Click on this to get the full view of the circuit like this. Now, little extension is required here for VDD. Okay. So, and the bulk of this PMOS is going to be connected to the source. This is source here. Same here. Case of NMOS also same, connect to the source. Take the bulk connected to the source. And here also take the bulk and connect to the source. Take the connection and connect it to the source. Okay, so now take this label net A. I'm placing everywhere. Later I will edit here, 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 everywhere, wherever. This is VDD is required here. And here also some connections are required. So, but later I will edit everywhere I'm placing this label net. So with the label net, I already discussed in my previous recordings of this LTSpice. Without extending the wire, you are actually making connections. So let's do this. This is VDD. So edit. This is for VDD. This is how we are editing. See, mouse, see the cursor shape. Here it is like this. The moment you take over label, it is changing like this. There, right click. Now edit. VDD. Here also it is VDD. Here also it is VDD. Okay, VDD edit is done. Now, what is required is here, if you look at this one, A bar B. So here A bar and this is B. So this, let us edit this one, A bar. So here, let's put A bar. And this is, let us edit this one. It is here it is B. This is B. And this is your B bar. B bar. No spaces. Simply B bar. So now it is A. If you look at this, it is A bar B. So this is A bar, and this is your B. So A bar B is done. A bar B is done. Now A B bar. A B bar. B bar. Now, now look at this here. A bar B. So A bar, A bar. and B. Now this A bar B is done. Now A B bar. A is there anyway. B bar. B bar. Okay, that is also done. Now this is your sum bar actually here. What you are getting is sum bar. This one is your sum bar. But the sum bar I am connecting here. Just click here, come down, left click again, go there, left click and right click. Simply left click will here the output we have to take. So this is actually your sum. So let us label that as this. So almost done. Anything I'm missing here, VDD, 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 VDD. Okay, ground I'm missing. So little extension here, ground for the ground. Take this ground, place it here, and here, here, and here. Take the wire, connect this bulb to the source. This bulb to the source of the invoice. Okay, so any other thing that I'm missing here? Uh, Almost done. Everything is perfect. Now let us go to this one, this version. So that is for the CO carry out. The two NMOS devices are in series. So let us take two NMOS devices in series. Series. So one NMOS here, one NMOS. Now two PMOS devices here in parallel. Devices in parallel. It's here, it's here parallel. And for inverter also we'll place here one NMOS is required. So take the NMOS here. Yeah. Okay, now connect here. This PMOS devices are in parallel and these are in series. So like this, uh, complete this parallel connection. Now connect this pull up with the pull down. Connected. So from the point where you have connected, extend that one. That is your output. So now here for giving inputs little wire extension. To zoom in, zoom out, that I spoke already. Like your mouse wheel, if you take it down like this down, you are doing zoom out. Now I'm making, rolling it upwards like this. Then it is zoom in. Okay. So, and this is for VDD here. And this extension down here for the ground. And bulk of this NMOS is connected to the source. Bulk of this NMOS connected to the source. Bulk of this PMOS connected to the source here of the PMOS. Okay, now you connect this inverter. Anything that I'm missing here? bulb. Bulb needs to be connected to the source here. And little extension of this here. Extension here for the output. This extension is for the making connections here. So now if you look at this one here, we require VDD and ground, VDD ground, AB, AB. Label net we can do. So let's do the label net. A, I will take A, I will place everywhere. Later I will edit it. Here also, you'll see here and here. So this label net here is CO bar it is, right? CO bar not required to keep, but for our reference, CO bar, this one. This CO bar is from this figure, it is this one. So it is not required to keep here directly. You can connect and then you can take the CO here. But for our reference, I am keeping. So connect this CO bar here. Okay. Now you edit this one, that is CO actually. This output is CO. Carry out. Now this is VDD. This is your VDD. This is also your VDD. Okay. Now this is your B. This is your B. So AB, and CO bar you have given to this inverter and you got this CO out and ground is required. Ground here. So now that we have completed CO also. Now we require A, B, two voltage sources, A and B, and then VDD. So three voltage sources are required. So let us take the voltage source, one for VDD and one for A, one for B. So little wire extension here. Then take the ground, place it here, 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 and then label net. You connect VDD, and I will place this VDD everywhere. Later I will edit. So here it is A, and this is B. And then the value required to be given. Right click here, this is 5, and right click here, go to advanced. Here pulse and T, V on 5 volts, and this is 10 nanoseconds, and this is 20 nanoseconds. Why is that I'm giving in NAND gate video? If you see, you will understand. Kindly see NAND gate recording. And then this one, go to advanced pulse. This is on 5, V on 5 volts. And T on here, it is 5 nanoseconds, and T period is 10 nanoseconds. So, anything else that I'm missing out here? Once check all connections done. Bulk is connected. Bulk is connected. It's connected everywhere. VDD is connected everywhere. Ground is connected everywhere. And the ground is connected everywhere. Values be inside here. Labels properly I have edited. A bar, B bar. And here also A bar, B, A, B bar. this A bar B here, this A B bar here, A B for this carry out here, this sum bar, CO bar connected here. Okay, everything is fine. Now to save this one, go to File, Save As. I told you have to create one folder somewhere on your desktop or some other drive, not in C drive, any other drive like, you know, D or any other drive. There you create one folder. Already I have created one folder here, lab demos. Open that created folder. Inside that again, create a folder, give proper name. What is this? Half adder. So I'll be giving half adder, no spaces. Please make a note, no spaces. Half adder. Select that, open that. Now you properly name here your schematic. This is half, and save it. Okay. Now, uh, done. Run this. So to run this, let's run till 100 nanoseconds. Now, uh, this window tile vertically. Let me close this one. Okay. So now what is that I have to plot? I have to plot this A. I have to plot this B. I have to plot this sum here. Plot this sum here. You just maximize this. Click on sum and click on CO also. You have to plot. Okay. Now see here, the tabs are there. After maximizing, you will see the tabs here. This is your schematic ASC, that is schematic raw, RAW raw. You will see their waveform, this one. Okay. So now here you right click, add plot pane for A, one more, add plot pane for B, one more, add plot pane for sum. So see the mouse cursor, how it is changing. Now left click, hold it, leave it here. Same thing for other signals too. And now to get the cursor like this, if you see the mouse cursor, how it is changed. Now you left click. This is your cursor. So go to first time here, first time interval. Here it is 1, this is also 1. When both are 1, 1. What is expected sum is 0, carry out is 1. So that is what we are getting here. Now drag this one here to other time interval. Here 1, 0. When 1, 0, your sum is 1. Your carry out is 0. That is what you are getting here. Now drag this to other time interval here. When your A is 0, B is 1. Again, sum is 1. Carry out is 0. Now drag this to other time interval here. Both are 0, 0. So sum 0, your carry out is also 0 here. So you are getting your results. This is how you have to explain in external exam. You know about the your waveform, whatever the output that you have got. Okay, you have to justify like the way I have just explained. Okay. So only your functional simulation you are doing here. Whatever the schematic you have done, this is functionally correct. So you are doing through it through simulation. Okay, that's how. So that completes our this half adder as well. So in similar lines, those who are having interest can work for remaining designs here. But lab point of view, so that is done. I think the series is completed for LTSpice. Okay. So to close this simulation, what I told, see, you have to be here on simulation result raw. This is dot extension is file extension is dot raw. There you be, and then there are two close here. This into one close, and this another into here. This is another close. So this second one. You just close this one. So that way you are actually closing the simulation. So you kindly practice. This is somewhat, when you compare with the inverter, NAND, OR gate, uh, little complex student point of view. So kindly practice this one. Pause the video, see how I am doing, and you also kindly practice this. So once or one or two times if you practice, then you will feel comfort with this design or any other design as well. Okay. For if you have still doubts, you please make a phone call or drop your comments in comment section. Thank you.